So this is number 3 in the Advanced Classical Mechanics Practice Final Exam. So problem number 3 out of 15. A disk of mass m, radius a, and moment of inertia I rolls without slipping on a horizontal plane. Its center, sorry about that, should be its center has coordinates x, y, and its orientation is described by Euler-like angles phi, theta, psi, where theta gives the direction of the disk's plane in the horizontal plane. So it's 5 parts. Part A, write the kinetic energy. Part B, derive the non-holonomic rolling constraints. Part C, explain why these constraints are non-integrable. Part D, use Lagrange multipliers to obtain the equations of motion. And part E, identify any conserved quantities and explain their origin. So from here, non-holonomic constraint in Lagrange multipliers. So rolling disk with non-holonomic constraint, non-holonomic constraint. Let the center of the disk be xy. Let theta denote the heading angle of the disk in the plane. And let phi denote or phi, whichever you prefer, denote the spin angle about the disk symmetry axis. So minimal coordinate set is Q equals x, y, theta, phi. And for a vertical disk rolling upright, the kinetic energy is T equals 1/2 m times the quantity x dot squared plus y dot squared plus 1/2 I sub theta, theta dot squared plus 1/2 I phi dot squared, where I is the moment of inertia about the disk's symmetry axis, and I sub theta is the moment of inertia associated with turning the disk about the vertical axis through its center. So the Lagrangian is L equals T, and the no-slip constraints are x dot equals A, phi dot cosine theta, y dot equals A, phi dot sine theta, and equivalently x dot minus A, phi dot cosine theta equals 0, and y minus A, phi dot sine theta equals 0. Okay, so moving along with this, we could say these are non-holonomic because they are constraints on velocities that cannot be integrated into equations involving only the coordinates x, y, theta, and phi. So the reason is that the direction of rolling changes with theta. A disk can roll around a loop and return to the same orientation while its center has undergone a net displacement pattern dependent on path. Hence, the constraints are path-dependent and non-integrable. So using Lagrange multipliers, lambda sub 1, lambda sub 2, we could have mx double dot equals lambda, my double dot equals lambda, mx double dot equals lambda sub 1, my double dot equals lambda sub 2. And here, I sub theta, theta double dot equals lambda sub 1 times this A phi dot sine theta minus lambda sub 2 A phi dot cosine theta. So I phi double dot equals negative A lambda sub 1 cosine theta minus A lambda sub 2 sine theta. Together with x dot equals A phi dot cosine theta and y dot equals A phi dot sine theta. These determine the motion. And since x dot squared plus y dot squared equals a squared phi dot squared, the reduced kinetic energy becomes T sub RED equals 1/2 the quantity ma squared plus I. That times phi dot squared plus 1/2 I sub theta, theta dot squared. So what we have here is phi and theta are cyclic in the reduced kinetic energy, giving here ma squared plus I, that quantity in parentheses, times phi dot. And that will equal a constant. and I sub theta, theta dot also equals a constant. So the disk rolls with constant spin rate and constant turning rate when no external forces or torques act. So the conserved total kinetic energy is going to be E equals 1/2 times the quantity ma squared plus I times phi dot squared plus 1/2 I sub theta, theta dot squared. And so the physical origins are going to be for 1 here, energy conservation, time translation symmetry. For 2, conservation of spin-related momentum, symmetry in the rolling angle phi. And for 3, conservation of turning momentum, rotational symmetry, and heading theta. So for here, we could say the center's motion is obtained from x dot equals a, phi dot cosine theta, y dot equals a, phi dot sine theta. And if theta dot equals omega sub theta equals constant, also theta dot equals omega sub, not theta dot. Let me start here again in this line. If theta dot equals omega sub theta equals constant, phi dot equals omega sub phi equals constant. So then from there, x dot equals a omega sub phi cosine of omega sub theta t plus omega naught, comma here, next component, y dot equals a omega sub phi sine of omega sub theta t plus theta naught. So for omega sub theta does not equal 0, the center traces a circle. For omega sub theta equals 0, it moves in a straight line. The rolling constraints are non-holonomic. Energy is conserved, and free motion consists of straight line or circular rolling depending on the turning rate. So that's all for problem number 3. My apologies if I mispronounced anything or miscommunicated anything. Thank you very much and have a great day.